And then in the vertical direction, we'll get n times cosine theta plus mu n times sine theta. Next up, we can equate this horizontal component with this horizontal component, and then this vertical component with this vertical component, and then solve for n, as we're not really going to need n in the calculation after this. So that's going to give us m times a equals, so I'll maybe factor in n out and see that we get n times sine theta minus mu cosine theta. So that's from the green overline. And then we have m times g will be equal to n times cosine theta plus mu sine theta, like that. But now we can take this second one and solve for n, and we see that we get n equals m times g divided by cosine theta plus mu sine theta, and then plug that into our m times a component. So let's do that. M times a equals m times g, and then this quotient of things with cosines and sines. So we've got sine theta minus mu cosine theta in the numerator, and then we have cosine theta plus mu sine theta in the denominator. Okay, so let's see what we've determined here. We've determined that m times a, or really the acceleration that needs to be applied so that this thing does not slide down. Okay, well, we can take this value for m times a and plug it in up here, and that'll give you the value of this f so that our block does not slide down. So let's go ahead and do that and see what we get. So that means our f will be equal to, so we'll have 3 times m times a, but that's going to be this thing right here. So we'll have 3 times mg times this whole thing here, sine theta minus mu cosine theta over cosine theta plus mu sine theta, and then minus 3 times m times mu times g, like that. So, since this is the force that is related to keeping this thing from sliding down, this would be the minimum such force that needs to be applied in order to keep this thing from sliding down. Now, before we move on to calculating the maximum such force, I want to point out that it's possible for no acceleration at all to be required in order to keep this thing from sliding down. You can think about that because of maybe the angle, or maybe this is like Velcro on this side and Velcro on this side. So that means this thing sitting stationary would have enough friction to keep that from sliding down. But then we would get no horizontal acceleration for the small block. In other words, this quantity would be equal to 0. But this quantity is equal to 0 when this numerator is equal to 0. But then this numerator is equal to 0 when mu is equal to tangent theta. But we have a negative acceleration when this thing is less than tangent theta. So that would be like even worse. We could pull this in this direction and it still wouldn't slide down. So just to reiterate, for mu values that are less than tangent theta, there is no minimum. And I guess I should say no, like, positive minimum. Okay, so let's get rid of this and then we'll look at the other case. So we just looked at the case when the force being applied is small, which means this green block would tend to slide down. Now we're going to look at the case when the force being applied is large. So if you're really shoving this bottom block to the left, then this green block would